The floor is yours.
Good morning. Okay. The joke for today. Learning to walk is a step-by-step process.
Yeah, it's good. It's good. You're all there one day. And then, that's an encouragement for this test, y'all. Walking was hard for you all. And now look at you. You're all pros. Expert walkers. That could be you with physics. It's new, it's hard, but one day, potentially sooner than later, who knows? You'll be an expert. Anywho, as you can see, our class is a little bit more, what's the word? Sparse. What a great word for it. Thank you. So if your group members have abandoned you in these trying times, feel free to find some new friends. As always, it is helpful to have people around you because what we're going to do today is, I've already posted this review document, but we're going to just walk through it, talk about the things you kind of need to know. As I'm doing it, I'll kind of make the decisions whether or not I sprinkle on problems, but there's basically summary slides where I'm just going to go through and say, hey, here are the things you need to know. It's nice summary. Obviously, can't include everything, because if it did, then I would have just done this in the first week and then just done a bajillion problems afterwards. So obviously, and in each kind of week has one slide to it. Obviously, I can't cover everything in one slide, so don't just view this as an end-all, be-all. But do view it as a nice summary. A nice summary of what we've covered, and the keys to summaries obviously don't include everything. So I always give that like asterisk. But it is handy. It is the main points. And then after that, we will just be doing problems. It's a good thing you're here. Reviews are always, if you haven't realized how useful they are, they generally are hopefully they're very useful. So we'll go through this. We'll see how long we really want to go with this. I do not expect to take the full 2 hours and 50 minutes. With the caveat that I will gladly stay here the full 2 hours and 50 minutes. If anyone wants to just stick around, and basically we'll just kind of treat it as office hours. So with that, I will kind of do a review. I will kind of go through some exemplar problems, some problems that I think are really good for you all to know. I'll toss out some concept questions here and there. We'll practice. Remember, that's how you should be studying, so that's how we're going to study today. And then, once we kind of reach a point where I'm like, yeah, I think we've covered what we need to cover. At that point, it'll be kind of up to you if you want to stick around and work on problem set problems or look at quicker questions, and we'll stick around as well. You're still paying me, so I'm not going to abandon you. But you, at that point, it'll kind of be I've covered what I want to. If there's things you specifically have questions about, I could talk about that then. So that's the plan. This Thursday, there is a finite chance that a hurricane will hit, and therefore, we won't know till Wednesday night whether or not things are going to cancel. I'm going to proceed as planned. I am not going to speculate. So I'm going to proceed as planned and proceed to have the test on Thursday. Obviously, if campus is closed, the test will not be Thursday. But that is pending that. If that happens, I'll send an announcement. If that does happen, without me even needing to send an announcement, the plan will be if campus is closed Thursday. If. Okay, say it as many times as I can. I don't want anyone to say, oh, he said we're not doing it. No. We are having the test this Thursday. Is the plan. If campus is closed, obviously we're not going to have the test. If campus is closed, we're not going to have the test. I'm just like, if I say it 10 times, I'm going to get less emails, right? That's the dream. If campus is closed, obviously we can't meet to do the test, at which point it will automatically shift to Tuesday. So if campus is closed, the test will be Tuesday. If campus is closed, it'll shift to Tuesday. We want to get this thing done, y'all. If we keep putting it off, that does not improve things. So that is a big if. Do not plan around an if. It's not a good idea. So do not plan around that. Okay, I say that. You can make contingency plans, hurricane planning, all that kind of stuff. That stuff's good. But as far as studying, just assume that it's going to be this Thursday, because that is the plan. That is the current structure. And if campus is closed, then you get a few extra days. All right. Unfortunately, 5x8 note cards. I brought them to my last class, and then I got caught up in answering questions at the end, and I forgot to grab the stack of them. So if you don't have a 5x8 note card, I don't have a 5x8 note card either. However, I am totally fine if you find a sheet of paper and you cut something that's 5x8. Just find a ruler. I will very easily be able to tell if it's not 5x8. A piece of paper is almost perfectly 5 inches across. I forget. No, it's not. It's almost perfectly 8 inches across. You'll need to shave half an inch. It's an 8.5 by 11 sheet. So you will need to measure it a little bit just to be fair to everyone. I don't want to give anyone any extra half an inch that people. 5x8. 5x8 note card. Yeah, you should be able to fit anything you need. All right. Any questions? Oh, and reminder to you all, you have a quiz that's due this Saturday. If you wait till Saturday to look at it for the first time, that's a terrible decision because you want to use the quiz to prepare for the test. So I give you all that time to be fair, but the reality is you should at least do the first attempt before the test because it's extra practice. All right, so let's just recap everything we've learned this semester. Again, it's a nice summary. It won't take us too long. It's going to be really boring. I'm just going to kind of point through some things, so there won't be really any solving, but it's just a reminder. Look how much we've learned. So we did vectors and units. Vectors, you got to break into components. I really hope you all are BFFs with right triangles at this point. So breaking things into components. If I give you all a vector that points in some random direction, and I say, if I give you a couple vectors in some random directions, so let's say we have a vector pointed that way, and then we have a vector pointed down. If you want to add those vectors together, that first guy, you have to break into the x and y component. And then, let's just call this A. That would be AY. That'd be AX. B here is only in the y direction. Great. Vectors are bread and butter of physics and engineering. Yeah.
So, and just a reminder, the direction, it would be from the end pointed down to the...
Yeah, so that's a good question. I'm actually going to ask one of those. Let's do it now. Let's just chuck a slide in here. I will kind of I tend to forget things. So better do it now. Find A plus B plus... how many do I want to do? D. All right. Angelina, draw me some vectors, please. There you go. All right, Angelina's going to draw some A, B, C, D. You're not going to do any numbers for this. It's just going to be, hey, here's 4 arrows. Show what they look like. The back end of it.
Just X.
Yeah. And if you want colors, there's a draw. All right, so can you add vectors graphically? That is a skill. Yeah, so on the test, the formulas will be given. If you all look on the Files tab, the formula sheet is on there. So you will be able to see exactly which formulas will be given on the test. I have printed the test already. Reminder, you all only need to bring a pencil, a calculator, your note card, yourself, and some ID with your name on it. All right, do it, y'all. I don't know what the answer is, but we'll figure it out together. How do you add vectors visually? And my reminder to you all, tip to tail. Tip to tail. Draw a vector, then where that vector ended, start drawing the next vector, and where that vector ended, draw the next vector, and where that vector ended. And the end result is from the beginning to the end. You gotta draw this, y'all. Doing this in your head, there's too much risk. Too much risk. Too much opportunity for silly mistakes.
No.
Oh, you did that on purpose.
No, that it's slightly at an angle. It's not curved.
Oh.
Nice, looking good, y'all. I'm so pleased to see it. We haven't practiced this in a while, so I'm glad to see that either you remembered it or you have been practicing it.
So you just put the vectors.
Yeah. The exam will be in this room during normal class time. So Thursday, 8 to 10:50 here. If you're late, that's just how many minutes you lose on the test. I'll still let you in, but you just won't get those minutes back. There we go. All right, so it's looking pretty good. Angelina, you made this problem. Yeah, grab a mic. There's so many of them. You each can have your own mic. We're gonna have to play Tracy.
All right. So, following the tip to tail, you got A. Take B up there. And then C comes right back down. And then you've got D, which is at a slight angle here.
And look, if it's not it doesn't need to be perfect. We're not looking for I'm not going to give you a protractor on a test to get perfect on these things. If I give you an answer, it'll be the answers will be very noticeably distinct from each other. All right?
Yeah, this is generally.
So if you're like, man, mine didn't go down that much to the right or that much down, as long as it's, within a reasonable amount. All right. Now, I haven't really mentioned this to you all, but because I haven't done, I need to have done a better job of this in future semesters. I will. A minus B plus C plus D. And all I have to tell you all, the only thing I have to tell you all that's different, in fact, let me copy and paste this slide so we don't lose anything. So the only thing that's different, I'm going to tell you all, so the answer is obviously not going to be the same, so we're going to erase the answer because it's not the right answer anymore. When you're drawing this, it's the exact same process, but when you subtract it, you just draw the vector, but exactly flipped 180. Because this, A minus B plus C plus D, is the exact same thing as A plus negative B plus C plus D. And a negative vector is just that vector flipped exactly 180 degrees. That's the really cool thing with adding vectors is subtraction. If you can do addition, you can do subtraction, because subtraction is just adding a negative. That is always going to be true. And so to this case, a negative vector is the exact same vector, but flipped 180 degrees. Take it and swing it the other direction. So that is pointed the exact opposite direction. So B is pointed to do the exact same thing. Yeah, I feel like I didn't do enough of these problems at the beginning, so I want to chuck one in here. It's not too much difficult to do. I just had to give you all that trick. Subtracting is just adding a vector that's flipped. Start with that distracted, but instead of B going up to the right, negative B is going to go. Yep. And it's otherwise, and then that's the only difference. How'd it go? Tip the tail. So it won't be the same answer as the last one. Yeah. You just gotta shift your B vector down. Yeah, that looks decent. Yeah, I don't know if more people will come in. Yeah. Yeah, exactly like that. Yep. Our yeah, exactly it. That's it. Yep. This. There's no way. I choose a little bit. Yeah. You know, I think it's roughly right around. Okay. Yeah.
With the tension,
Oh, there was some conflict. Because I gave you all the exam date. If things that you'd planned around that conflict with that, then it's that's why when things get shifted, it ruins everything. But we'll do. Yeah, I'm not gonna penalize you for not. Yeah, there you go. Feel free. All right, just to give this one really quickly. So A is to the right. The only trick to this, and I guess I should draw A more accurately. The only trick to this is B goes back. Oh, I didn't give myself enough room. So A is here, then B goes the exact opposite direction. And then C goes down that way, and then D goes very, very tiny bit. So, something like that. Something like that. There you go. And that is A minus B plus C plus D. And there will be cases where you subtract vectors. That is a thing. So, and technically all these should have little hats on them if they're vectors. But doing that notation on a computer is a pain, so you get what you get. All right, awesome. Fantastic. Vectors, make certain you're good at them. It is a skill. We will also, I'll give you all some random problems later on about adding them. I mean, there's so many in the problem sets. Gosh, so many vector things. All right, base units, you need to remember those. Kilogram, meters, meters per second squared, seconds, meters per second, all that goodness. We'll do some practice with it. Basically, we'll just sprinkle that into all the problems I give you today, where you'll have to convert things. Yeah, the unit conversions you need to know. The unit conversions you need to know are, you need to be able to go, I'm just going to give it in terms of meters, but it applies to everything. You need to be able to go from centa, milli, and kilo. Those are kind of the bread and butter. Centa, milli, and kilo, that's the bread and butter. You could make an argument maybe for mega, but other than that, I don't know. Leah's gone. Angelina, have you ever seen hessa, hecta, dessa in your life? No one uses this.
Do we need to know what any prefixes mean besides those ones?
No. Centa, milli, and kilo, you'll be good to go for this test. Now, Angelina and I are both in the physics field, so we're a little bit like, we only have exposure to physicsy things. We have not seen dessa, hecta, deca, but there is the off chance that in your field that you go into, forensics, engineering, whatever, maybe they use them. I have never heard really, hectares I think people use, like hecta acres. I don't even know if a hectare is a hecta-acre. Probably. Yeah.
So on the problem set we have like stuff like nano.
Yep. So the problem set. Oh, nano is nice to know. Micro is nice to know. It's not going to show up in this class, but it will show up in physics too. In this class, centa, milli, kilo are good. The problem sets I always give you all a bit more than I'm going to test you on, and that's purposeful. But this is the ones you all need to know: centa, milli, kilo. And you need to remember that kilogram is the base unit for mass. Kilogram is the one funky one.
Yeah, and also for like scientific notation, like when we make it scientific, do you want it to like 1 decimal point or 2?
Yeah, so the question is when you do scientific notation, how many decimal places? 2-ish, 2 or 3 is the rule of thumb. On the test, on the multiple choice, there's not going to be any answers. I'm not going to give you a answer that's like 2.1 and then another answer that's 2.2. I'm not going to do that. The answers will all be more than 10% different from each other. On the free response, same thing. When we're grading your thing, we're not going to be nitpicky and be like, oh, you put 2.1 instead of 2.21. Like, if you're in the ballpark, you did things right.
How is the exam difficulty compared to the quiz and problem set?
I would say that the exam difficulty is similar to the quiz difficulty. So the exam difficulty is similar to the quiz difficulty. Those are kind of 1-to-1. And then if I called the problem set a 10 out of 10 difficulty, which is not, but let's just say it was, just to give you all, let's standardize our scale. I would rate this test at like a 8 maybe, compared to the problem set's a 10 difficulty. This is an 8 out of 10, maybe 7, maybe 7. As I told you all, the practice problems I give you are going to be harder than the test itself because the alternative is the opposite. And that's much worse. So yeah, it's much better that I give you much more challenging things. And if you can do all that, then you can do this versus the opposite. And I never want to try to like make them exactly equal because then what if I'm wrong? What if the test ends up being a little bit more challenging? People are like, oh, it was worse than that. So I'd rather err on the side of caution, and I push you all a little bit further. And even I actually realized this semester I need to even include a little bit more challenging problems, not even to make things, not because I'm going to test necessarily on those, but because it's good to give some of the people in this room, if you're like, man, this stuff's easy, it's good to give a little bit of a farther reach for some people. So that's something for me to think about in the future. The benefit of that as well, for people that already know it, by having it a little bit more difficult, maybe it pushes you a bit more, whatever. All right, so vectors and units, they show up in everything. So like this is the first week, but honestly, this shows up in everything after this. All right, 1D kinematics. Position, displacement, velocity, acceleration. You need to know what they mean. You need to know position is where you're located. It's a vector. Displacement is how far you've traveled from your initial position. That's a vector. Velocity, acceleration. You need to know the relationships between them. So you need to know that acceleration is the derivative of velocity, which is the derivative of position with respect to time. Lots of problems on that we've done. There's the equations. We love them. You need to know how to use these equations. You need to be able to identify your givens and your missing and all that jazz. Hopefully at this point you all have realized that it's not about looking at a problem and saying, I use this equation for this problem. Hopefully you haven't fallen. That's the trap that a lot of people fall into is in the beginning of this class, it's the most common thing. They look at the question and they immediately say, what equation do I use? That is not how these work. How these work is, what do I have? What do I need? Then you find the equation that satisfies those conditions. So it's not like if I have a specific problem, I use this kinematics equation. Or if I have a specific problem, that is not the mindset. You do not want to be studying these problems and saying, oh, I have a problem. This guy's running. Oh, I'm going to use this equation. No. It is what is given, what is missing. Find the equation that will let you find the missing pieces, especially when it comes to the kinematics equations. This is a toolbox. It's a bunch of different Allen wrenches of different sizes. You got to figure out the right size Allen wrench. Yeah, so so on the test, let me show you all where this formula sheet is. Yeah. Now, on the test, you all will have the following formulas printed on the Scantron. The Scantron will have the equations written on it. And it's these exact equations. I literally copy and pasted them over. So this is in Files, formula sheet. There it is. Literally, I copy and pasted this. This is what you'll have on the test. This will be on your Scantron. So you all do not need to bring a Scantron. I print it for you at the last page of your test. So on the test, the last thing I'll tell you all when you come in here, once you have your test, I'll say rip the last paper off because that's a Scantron. The Scantron and the free response will be separated for grading purposes. I scan the Scantrons. You can guess why. You'll have this on the Scantron. So that'll be convenient. There will also be a piece of scratch paper stapled to your test as well. So you also have some scratch paper if you need extra, I have paper in the corner. But scratch paper, everything will be kind of on the test. On the test, I've also put margins on the problems so you have space to solve them and try to make it as user-friendly as possible. But this is it. Yeah, this is the formula sheet. You all can see it. You can make certain when you're making your 5x8 note card, I recommend not writing stuff in your 5x8 note card that's already on here. Up to you if you want to, but this will be given. Word for word, literally copy and paste it. It's going to look just like this. All right. It's a good question. All right, so these will be given. And yeah, you need to know that acceleration due to gravity is always negative 9.8. All right, now let's ask some random conceptual questions just chucked in here. What is the acceleration of an object? All right, let's give some preface. I toss an apple straight up. what is its acceleration on the way up? There you go. You know what? I tossed an apple straight up with a velocity of 5 meters per second. There you go. Try it out. Super challenging. I'm going to give you all 20 seconds for this, which is a hint. If you need more than 20 seconds, you think in the wrong direction. What's signal? What's signal? Oh, there we go. What are the units? Alright, what do y'all think?
Wait, so
On the way up, what is accelerating? Any rockets attached to it or anything?
yeah, so
So what's the only thing affecting
if
it?
position
Gravity is the only thing affecting it. What's the acceleration of gravity? Alright, what's the answer, y'all? Negative 9.8. Always. Hey, what if I asked you the acceleration at the highest point? What's its acceleration when it's at the highest point? Negative 9.8. But that's good. The velocity is 0 at the highest point. The velocity is 0 at the highest point. But the acceleration at every point in the air. Let's draw a beautiful picture of this. Here's my ball getting tossed. It has some velocity here at the highest point here. What's my acceleration at this point? Negative 9.8. What's my acceleration at this point? Negative 9.8. What's my acceleration at this point? Negative 9.8. Really what just hammering into your head? Don't mix up acceleration and velocity, y'all. It's classic mix-up. So, just remember that. That's a very important concept for you all to remember, that gravity affects all things by negative 9.8. I didn't tell you all the mass of this ball. Does it matter? Well, it's an apple, I guess. But yeah, doesn't matter. The mass doesn't matter when it comes to acceleration. The mass doesn't matter when it comes to acceleration. So, there you go. Fantastic. That's just a really, really important thing. And yes, do remember at the highest point, velocity is 0. All right. 2D kinematics. Oh my gosh, I didn't put this in bold.
You don't have any more notes, right?
Oh. If you came in later and you missed my announcement on it, I'd forgotten my note cards in another class. It's very sad. However, you don't need to go buy out some note cards. If you cut a sheet of paper to a 5x8 size, I'm content with that. You do need to measure it though. I do have a rule. My tape measure's in my office. Maybe I'll bring it to class. That'd be a little mean. Oh, we got a meter stick here if I have to. But yeah, I'll be out of tell. I'll bring a note card to class and hold it up to yours. And if needs be, I'll just trim off the side of it. Who knows what you're gonna lose? All right, 2D kinematics, y'all. You gotta split things into X and Y. Like that's what you need to know. X and Y gotta be split up. Time is the only variable that carries across them. It's the same equations from 1D, but you have the pleasure of doing them twice. What a joy. What an absolute joy. All right. And then there's a few key points. Remember that velocity in the y is not constant, so there is an acceleration only in the y direction. Only in the y direction. In the x direction, a is 0. And remember that direction matters. Up is positive, down is negative, right is positive, left is negative. And let's just make a problem. These problems are so easy to make, y'all. So easy to make.
That can get to cancel the units. If you ask, if you drop something and it accelerates at 9.8 meters per second, or does it travel in 2 seconds? Because then they can do the second square to count those second
Yeah, we could do that one. Yeah, I'll check that one in
It's
here.
not something that people think of all the time, but it's really easy.
Yeah. Let's see. Where do I want to start with this with a object? I throw an object with a velocity of 5 meters per second at an angle of 10 degrees. I think I am going to make this problem a little... The object starts at a height of... how tall am I? A little over a meter, 1.2 meters. Maybe my arm's up here. 1.3 meters. That's about me standing on the ground throwing it. The object starts at a height of 1.3 meters. If it hits a wall, how far is that wall from me? 3 meters? 3 meters away. What will be its height? All right. There you go, y'all. I throw an object with a velocity of 5 meters per second at an angle of 10 degrees. So that's kind of horizontal-ish. Keyword-ish. The object starts at a height of 1.3 meters. If it hits a wall 3 meters away, what will be its height when it hits the wall? So, first step, draw a picture. Next step, write down your givens. Next step, what are you solving for? And yeah, no, I can totally give that one.
It's just easy, but
Oh yeah.
they know they cancel units.
Yeah, and that one, I don't even know if you need to count because it's how far is it dropped after 2 seconds.
Yeah.
They just can use the xf equals x naught plus v naught t plus 1/2 at squared
Okay.
because they know a, they know t. So
You could also just do times 2 squared, right? Cancel the second squared with the second squared. And then that'll get you the same
cancel this.
times, because it's meters per second squared. If you multiply it with the second squared,
Oh.
that gives you the meters.
Yeah, that's what you're doing. You're doing xf equals x naught. You are using
but
that.
you just
But you do need a 1/2. You still need the 1/2.
you need the 1/2 still.
Yeah, the derivation ends up spitting out that 1/2 because you have to integrate.
Oh
Yeah. So you'll be off by a factor of 1/2.
Yeah.
But it's good. You effectively see why that equation works though in some capacity. But you do lose that 1/2, which will make your answer. It is a classic when solving physics problems to be off by a multiple of 2. Like it just always happens. That was one of our go-to statements is where did that factor of 2 come from? In grad school, that was always happening. I don't know. Alright, yeah, let's see some pictures, y'all. That's the first thing I'm gonna look for. And I'm gonna tell y'all, I have no idea if this thing starts it's higher or it's lower. We have to do the math to figure that out. I don't actually know. I'm also hoping this problem is reasonable. Yeah, turning out this it'll make it that far. There is a chance it can hit the whole ground. I've done that, yeah. That's a problem. That was the problem. I didn't get my Yeah, that's a valid, totally valid. Yep, you get to define the origin. You can do vice versa as well. And the initial. Oh, of course. Yeah. I avoid at all costs. Honestly, oh my God.
Oh, so you have to like, and you're not.
Oh, yeah, that's what that's the contract for. It's just one. Perfect. I was like, I don't care about stuff. I don't care if it's not good or not. That's not what I'm saying. This is one of these. No, so I don't care for that. That's why I don't care about I care about steps 1, 2, 3. Step 4 is So easy. There's so many things you gotta plug in places, and it's so easy for the wrong slide. Don't forget. So to give you all some checkpoints, here's the object. It starts 1.3 meters above the ground. Then there's a 5 meters per second. That's V naught. My angle here is about 10 degrees. 10 degrees is very hard to draw because it's not very high, but there it is. And then their wall, and I did see some people do that parabolic path, which is awesome because that is the trajectory it's going to take. Now, I cannot tell you all, until I do the math, I don't know if this thing's going to land higher, at the same height, lower. I actually have no idea. Oh, is it really?
Yeah,
Is it?
0.1 meters.
Great, it didn't hit the floor though. I was really worried about it ending below the floor.
Yeah, that
When you make up problems, that is a risk. If I didn't throw this thing fast enough, it might not make it to the wall, but I told you it hits the wall, so don't worry. All the test questions, it's multiple choice. I had to figure out the answer.
Yeah.
I didn't have a choice. All right, but good news, someone did solve it, and they did find that the answer is somewhere. But we don't know that until you solve the problem. That's why math is useful. That's why you can't just rely on concepts. You got to do the math because the math is a necessity to be able to actually figure out the final results precisely. It's fine. It's fine. It makes it. Alright. I have two people have the answer of 0.01, so I'm just going to trust that that's the answer. If anyone gets anything different, let me know. It makes it. That's all that matters. Man, what were the chances? Yeah, I was a little worried about it being, I guess 0.011 when I saw someone had. I haven't done the math yet, so I don't know for sure. But yeah, next step is the givens. So I've only drawn the picture. Next step is what is given. You need to list those out. If you're not sure how to proceed, that is the next step. That's how you do these. There is a recipe to solving all physics problems. Solving all problems in life. Imagine the problem, picture, whatever, what's given, what's missing. That is the critical thinking process. Oh, it's 101? Yeah. All right. So the givens, we have the magnitude of initial velocity. I put those little bars around it to show that's the magnitude. It includes the x and the y together. We know that xf equals 3 meters. We can say, so you can define your origin. You can define, remember the first question I asked you all in this class was where was Dimlo Duck located? That was one of the first questions. So we're going to decide that we start at 0. We're going to decide that we start at 0 because why not? Nothing's stopping us. We're going to say that my initial y, we're going to say the ground is 0 because that's a classic, right? That's always what people kind of default to. So that means my initial height is 1.3 meters. Now, when you're writing your givens, you should break things into components here. Do it sooner than later. Do it sooner than later. These are all in component form already. X and Y's. Yay. But this is not. My initial velocity is not in the X and Y direction, and therefore it is useless as is. I mean, I guess there is technically stuff you can do with it. When we get to energy, you can do stuff with it with energy. But as it stands for these problems, you have to break this into x and y components, i.e. v initial x and v initial y. And if you're not sure how to do that, call one of us over so we can work with you individually, because that is a incredibly important skill to solve this. Yeah, how do you do it? All right, we got a triangle. So we have our initial velocity triangle. I'm just realizing, so it's not hidden. So it's going to be our velocity. So we draw our velocity vector, and then you just turn it into a right triangle. On one side of the triangle is the x part of how right and left it is, and one part is the up and down. That's all we're doing. Yes. Alright, and then we know this is equal to degrees. We also know one of these sides, which is the side that is equal to y. They give you the magnitude of velocity, also the biggest side. The magnitude of it, the total of L, that's always the biggest side of the triangle. Yep. We know that. And then we can see on that triangle, I have a part that's pointed left, right, and I have a point that's pointed up, down, left, right part. And then the x component of that, so in this case, we'll label this the initial. And then this will be the initial y, and this will be the initial x. Any vector you can break up like that. Any vector. There you go. And now it's just we know this number. This is just true. I thought this angle. Oh, it's so good to step. Yep. That is a bread and butter skill that'll transfer across. We're gonna use that again and again and again and again and again. All right. So in this problem, you draw the triangle. Again, it's always important. Like breaking vectors into components is a skill that you are going to use so much, not just in this class, but in future classes. Breaking vectors into components it's a bread and butter skill, y'all. It's going to happen again and again and again and again. And to do that, you look at this triangle. I give you the initial velocity. I give you the angle. And it ends up being that this is V naught times cosine of the angle. And this one's V naught times sine. And I remind you all, it's not always cosine for x. It's not always y for sine. It's because the opposite is the y component. Sine gives you the opposite. The x component is the adjacent. X component, or cosine, gives you adjacent. I've said this a bunch of times, and I've been very pleased with how you all are doing on this, not falling into that trap of x being always cosine and y being always sine. Too many people fall into that trap, and you get the completely wrong answer. So, if you do that. Anyway, all right, step 2. What are we solving for? We are solving for the final y, which can be written 2 different ways. Those are both the same thing. And this is where the second part, the y of t, reminds you all, in these problems, you basically always need time. Just like, even if I don't tell you, I never told you to find time in this problem, you're going to need to find time in this problem. That is just, it's the only variable that goes across x and y. You find the time. Now to find the time, you have to find the limiting case. Is it the horizontal or the vertical that determines that time? You have to make that decision.
Is this the answer?
You have 0.009, which is very close. That's a good one. Yeah. You have 0.0099. The answer is 0.0101. That is good.
Okay. Should I have put like?
You're fine. Your answer is fine. You're within 1 to 2. Yeah. Sure.
Yes.
Yes. an equation. What is the angle if it's perfectly horizontal? In this case, it's 10 degrees. So as I go horizontal, that's going to be 0. Yeah.
Yeah, this
So
one's really nice. You can like
the x component,
multiply
if we kind of use this big
fractions
triangle,
and
the angle is 0.
fractions.
The side of 0 is 1.
I have
And sine of 0 is
I have a
0.
TI-84 and it's not nearly as user friendly for just like
It's 10 degrees above Yep. That angle of 10 degrees is key. What was funny enough is the equation all work for if it was perfectly horizontal, 0, and it would actually still work out. Yeah, if the angle is given, yeah, you have to break the next one for that reason. It's very nice when it's just purely horizontal, but that's really hard. It's impossible basically to throw something perfectly horizontal. Okay. Are you working in the X or are you working in the Y?
Yeah.
Oh yeah, that's only for the Y. Yeah, you should never have negative exponent with X's. Good. Yeah, so just to kind of wrap this up a bit, and then you can kind of keep solving this on your own at some point if you want to. In this case, the x is the limiting factor. So you're going to use xf equals x naught plus v naught xt plus 1/2 at squared. What's my acceleration in the x direction? 0. Always for projectile motion problems. It doesn't have a rocket attached to it. Nothing is pushing or pulling it in the air. This is a very important thing to remember, y'all. When something is in the air, nothing is pushing or pulling it, assuming no air resistance. Assuming no air resistance. So we'll talk about forces and all that stuff, but that's just a good thing to remember. So, long story short, this term doesn't matter. You get the time, and then you do the exact same equation. You do the exact same equation, but you do it for the y direction. 2D kinematics is just 1D kinematics twice. And then we just use our y, and I'm going to even put it two different ways. Y naught plus y initial, v initial y. Yeah, so the most common mistakes I see on these problems are very much just putting the wrong variables and putting the x variables in the y equation or the y variables in the x equation. I see that all the time. That is the most common mistake. So remember the line, you got to keep them separated. Think of the song. You got to keep the x and y separated. They don't get along. They're apples and oranges. They're both fruit, but they're not the same. All right, and then you go from there, and it's a good time. But there you go. If you all can do this, so this is one where the x is limiting, but if you all can do this, all projectile motion problems basically boil down to this process, y'all. Givens, missing, picture, x, y components, all that jazz. There is so many examples in your all's problem sets for projectile motion. So if you are struggling through it, just go through them again. It might not sound fun, but it is the procedure. It is the process for learning it.
So I'm just wondering if we'll actually have to do any calculus in the exam
So calculus-wise, the level of calculus you'll need to do is the same calculus I've given you all in the problem sets. So if we look in the problem sets, the calculus that I've given you is taking the derivative of a position function to go to a velocity function and take, let's do a calculus. This is technically a one, let's make it a 2D kinematics problem. A car's velocity is given by v of t equals, let's give some reasonable numbers. 3t, that's fine, plus, this is going to be nonsensical, when I say nonsensical, it's fine. 2t squared. So this velocity is changing with time. It is changing with time in a quadratic way. That's fine. They're hitting the gas at some points or taking their foot off the gas at some points. That's allowed. I'll tell you all, this is a not constant acceleration. And you know what? Let's make this worse. I got to break it into vectors. 1 second. I have to insert an equation because it's the only way to put that I hat. V of t equals 3t. Yeah, this is the joy. Anytime y'all see any formatting I've done on that problem set, this is what I suffered for you. And then I got to find the J hat. Okay, so I'm going to actually give you all a few problems with this. 1, what is the magnitude of the car's velocity at 2 seconds? Let's start there. This is a vector with x and y components. This is a vector with x and y components. Be careful about that. Case in point, the answer is not. The answer is not. The answer is not 18 meters per second. I think, is that what will happen? No. 4 times 2 is 8. 8 plus 6 is... It is not 14 meters per second. 2 plus 2 is 8. 8 plus 6 is 14. Yeah. This is why you don't try to do things in your head. It is not 14 meters per second. If you get 14 meters per second, you have fallen into the trap of not separating x and y. This is a vector with x and y components. Except the second term, the y component might be 4. Oh, yeah, 2 times 2 times 2. Yeah. The key to this is realizing x and y are separate, and this is just a variable. This is in vector notation. This is vector notation. Oh, I have no idea what the answer is either. It's some number bigger than it. Yeah. No, there's no way you can do this in your head. You did. Does it actually end up nicely? Yeah. Is it? Oh, it's a 3, 4, 5 triangle. Oh, what a blessing! Yeah, what a blessing, y'all. We got lucky that our answer is nice. The answer is, I guess, 10 meters per second. Yeah. Oh, what a nice. Not planned at all. If you're not sure to get this, call us over. We'll be lurking, but we can try to figure out if you're confused, or you can just tell us you're confused. Yeah, I'll put. Yeah, I'll put. Yep, it's not great. Yep. All right. So for this one, y'all, we're gonna plug in the t of 2 seconds. So that is gonna give us 3 times 2 I hat plus 2 times 2 squared j hat, which is going to equal 6 I hat plus 8 j hat. You cannot just add these together. Let's draw a picture of what this looks like. This says the velocity is 6 in the x and 8 in the y. You cannot just add those together. That is the key. The key to this problem is just taking and realizing this is an x and y, and then shifting your brain to, okay, there's an x and y component. Once you realize it's this, then the final velocity, the magnitude of the velocity will be 6 squared plus 8 squared, which is not 10 squared, it's 10. But yes, that's what this problem is doing. I can almost guarantee every person in this room knows if I give you an x and a y component that you need to use Pythagorean's theorem. You just need to recognize that this problem has an x and a y component. That I hat and that j hat, they are very subtle, y'all. It is so easy for your eyes to just look right past those. But if you look right past those, it's a language, y'all. And if you go right past those, you're missing letters. And words change if you forget a letter. Whatever. So, to that end, x and y component, you've got to keep them separated. You can only combine them this way. Now, building on this, the reason I originally asked this question is, what calculus might you expect in this? My question to you all now is, what is the position vector at 2 seconds? What is the position vector at t equals 2 seconds? And then following up on that, what is the magnitude? What is the displacement? Magnitude of displacement at t equals 2 seconds. Assume we start at the origin. Assume that, well, actually, you don't have to assume. Actually, you do. Car starts at 0, 0. You would in this case. And if I didn't specify that, it'd actually be involved. Well, displacement, you wouldn't have to. Position, you would. Yeah, displacement, you wouldn't have to. Position, you would. So I did actually have to define the origin, otherwise you get a plus C. Unless I said displacement. So this is also asking, do you know how to write vectors in x and y components? Do we integrate it for 2 over 3? That is the question. Give that is the easiest way to remember that. No, there's also going to I also did yeah, and that works a bit. So, yeah, dividing by seconds. Getting rid of the second. I don't know. Yeah. Same. That's still valid. Yeah. Whatever helps you. Like all those are valid. All those stuff. Yeah. So that's why I gave you the car starts at 0, 0 meters. And then don't lose your I hats. Don't lose those. Yep. So my car's at 0, 0. You can use those boundary positions. When time is 0. What is this equal? So therefore C is also right in 0.
Yeah.
So each of these actually have their own.
It is just like.
As weird as that seems, each of them gets their own.
Yeah. It's very easy.
Yeah, I could have made this worse. Maybe I should have. Maybe I should have said the car starts at a different position.
Yeah.
That would have stretched their brains a bit more.
You can recognize it just like.
Sure. For displacement, it's no problem.
Yeah.
All right. So the key here, y'all. Do I take a derivative or an integral? Integral. To go from velocity to position, I take the integral. So to get position with respect to time, I'm going to integrate my velocity with respect to time. These are vectors. Do not lose your i's and j's. Do not lose your i's and j's. If you lose your i's and j's, you will get the wrong answer. So you get 3t squared over 2 plus c Each of these is its own integral and therefore gets its own constant. X and y are separate. X and y are separate. X and y is separate. So this integral of 3t I hat plus 2t j hat is actually two integrals, each with its own constant, plus t squared plus c j hat. All right, this is where boundary conditions come in. Boundary conditions come in. It says the car starts at 0, 0. So at time equals 0, my position in the x direction is 0. At time equals 0, my y position is 0. Because of that, because of this part right here, C in this very specific problem will be 0. Did I mess that up? Oh, thank you, thank you. I was wondering, I was like, oh, that's such a nice integral. Yeah, I was like, that looked too nice. 2t cubed over 3. Thank you, thank you. All right, so you know what? I'm actually going to show you all this boundary conditions thing because that is important. You have to, when you do an integral, you need boundary conditions to get a definite integral. So at x of 0, we get, 3 times 0 divided by 2. You know what? Let's actually write this. We know it should be this. That's based on that. So therefore, time is going to be 0. So the first term is 0 plus c I hat plus 0 plus c j hat. Okay, so yes, c is 0. So yeah, whatever. Those are 0. Fantastic. But that is important to have that skill. I should have actually been meaner, and I should have said the car starts at 1, 2, or some nonsense like that, and then confused everyone when they got the wrong answer because they forgot about the boundary conditions, but I didn't. So there we go. Anywho, x of 2 equals, so c is 0, so we'll take this, and we'll do things with it. So you do get 3 times 2 squared divided by 2 I hat plus 2 times 2 cubed divided by 3 j hat equals 2 squared is 4. 4 times 3 is 12. That's 6 I hat. Did I mess that up? No, we're doing good. Tell me if I'm wrong. Doing math in your head is a terrible decision. Like, I should be using a calculator for this, but here I am. All right, 2 cubed, 8 times 2 is 16. 16 divided by 3 is 16 divided by 3. That's what it is. All right, great. There's the answer, y'all. Now, to get the displacement, if I started at 0, the displacement will just be, my initial position is 0, so you do just end up subtracting these. Displacement is delta r equals xf minus xi, all those things. Ends up just being 6 squared plus 16 over 3 squared. I don't know. Y'all tell me. You did it. What'd you get? 8.00. Does the 2 go there? Sure. We'll do something like 2.8. Put a 3 there. All right. Great. There you go, y'all. And you know what? If I was we could continue this if we really wanted to, and I could say, what's the acceleration at 2 seconds? And then we take the derivative of the velocity and whatever. But if you can do B, the new boundary condition. That'd be.
Would you have to give different boundary conditions?
No. Taking the derivative, you don't care about boundary conditions. Yeah. Taking the integral, you care about boundary conditions. This one you don't. All right, great. Here's an example where you will need calculus, and I do need you all to know calculus. Like later on in this class, we're going to see a bit more calculus when we talk about work, when we talk about center of mass. Calculus is a very important tool. There's a reason that Isaac Newton invented it. It lets you do things you couldn't do otherwise. So, all right, great. Onwards. Tricks for projectile motion. These are just some things. Remember, if you land at the same height, if you're landing at the same height you started with, the total time is the time to the top times 2. The initial y velocity equals negative y velocity final. Vx is constant. than, things we've talked about. This is just reminders. Yeah.
So,
No, it's good.
again, like the final velocity is not 0. It's right
Yes.
before it.
Yes. The final velocity in projectile motion problems is not 0. That is also a classic mistake. People often, it hits the ground, so it stops. Well, okay, yeah, but we don't care about that. We don't care about when it hits the ground. We care about right before it hits the ground. Because that's like saying, I throw a baseball at your face. How fast does it hit your face with? And you say 0 meters per second because it stops. No, it does not hit your face with 0 meters per second. So obvious. Like you can see why we would care about how fast something is going. A rocket is coming down to Earth. How fast does it land with? 0 meters per second. Eventually, sure, yeah. How fast is it going right before it hits the ground? That matters. If you're real smart like SpaceX, you can make that 0. Before then, that thing did not hit the ground at 0. Anywho, all right, great. Circular motion, just remember these things. Remember these equations. We'll do a really quick question with this. AC is always towards the center. It's literally called centripetal acceleration, center acceleration. V is tangent towards the direction of motion. Let's make a circle. All right, I got an object going counterclockwise. Draw the direction of velocity and acceleration at this point. VT, question mark. AC, question mark. Draw them. Draw the direction of the velocity and the acceleration when it's at the bottom. The rules are right there. It's one thing to know the rules, another thing to apply them. And good news, y'all. We are 2.5 weeks through at this point. Yeah. No. I haven't given you any. Yep, just try it. Draw some arrows. Do not calculate it. I haven't given you jack squat to calculate. So you just draw the arrows. Just draw the arrows. Yeah, make up numbers if you want. Your answer will also be made up. Tangential velocity. You better draw a straight line for BT. You better draw a straight line for both of these. They're vectors. We have never drawn a vector that's curved. It does not exist. Vectors are straight lines always. You can't have a curved vector because what would be its like? Which way is it pointed? I don't know. Depends which way you're on the line. Vectors are always straight lines. These are vectors. All right, y'all tell me which way does A point? Which way does it point? Up, down, left, right? Oh, thank you. Look at that comp. Towards the center, y'all. Centripetal acceleration. AC points centrally. All right, great. Now, VT, tangential velocity is the direction it'll go if you kind of released it at that point. Which way does VT point? Up, down, left, right? To the right. V points to the right. Remember the strat, y'all. The strat for velocity. You draw a little line. You just draw a little line, and then you decide which way that line should go. Right or left? If my thing's going counterclockwise, at this point, it's going to go this way. Oh, no. All right. Great catch, y'all. There's a typo on here. See if y'all can figure out the typo in my equations. One of these equations is wrong.
Oh, acceleration.
Nice work, nice work. Whoever spotted that, that is a typo. A is just VT squared over R. What happens if you multiply A times M? Force. You get force. I accidentally put the force up there like a chump. Yeah. I'll give you a high five. Through the air. A point on the test. You know, you'll get the point because you'll know the equation. You've earned the point. Isn't that more meaningful? All right. All right, great. Newton's laws. You do need to remember these laws. I'm not going to test you all. I'm not going to say, what is Newton's first law? And then have you pick the option that is Newton's first law. I am not going to give you a problem where I say, an object crashes into the wall. Which of Newton's laws explains what's going to happen? I'm not going to ask that. But I will ask questions like the clicker question I gave you all. A truck and a fly hit each other. How do the forces compare? They're the same. Newton's third law, for every force there's an equal and opposite. I will give you all problems where I say I double the acceleration on an object with half the mass. How does that affect your acceleration? How does that affect your force? I will give you problems like you've seen up to this point, applications of these laws. I could give you a problem saying a bullet gets shot in space. What happens to that bullet's velocity over time? It doesn't change. Because Newton's first law, an object in motion stays in motion, an object at rest stays at rest until a force acts upon it. So, look at the clicker questions. Make certain you all can do those. The ratio problems, let's chuck one of those up here. I will give you all the ratio problem because we only did one of those in class. And so it's a good. So I push two objects with the same force. If object A has, give me a number, 7 times the mass how will the acceleration compare? You know what? Actually, let's make this worse. I have two objects. Object A has 7 times the mass, and I put as object B, and I push it with, give me a number, 3 times the force of object B. How do the accelerations compare? There's 2 ways to solve this. One way is using the equation, and I'll kind of walk you all through that way. And if you're like, man, I'm not sure what to do, there is a brute force method. Make up numbers. If you're like, man, I love numbers, then make some up. Make up whatever masses you want, but make certain they follow these rules. You can make up numbers and problems if I haven't given them, like in cases like this, if this changes, how does this get affected? You can make up numbers. Nothing stops, as long as it follows these rules. As long as object A has 7 times the mass of object B, and as long as object A has 3 times the force of object B, as long as your numbers satisfy that condition, you can do that and compare them. That is an option. That is kind of the brute force method. And then I'll teach you all the equation-y method. So mass of A is 7 times mass of B. This is very useful to write down. These little things are very handy to write down, the relationships between them. Just putting in math, what is written in words, interpreting it from words to math. Make certain you know how I made those, because that is a skill. Being able to write down what I just did, when you look at it, you're going to be like, oh, of course. But being able to write that down is key to solving these types of problems. And it shows your math literacy.
So mass is okay.
Yeah. 3 times harder. So we find our equation, and then what I recommend you all do with this equation, write in terms of the variable we care about. What variable do we care about? What are we ultimately comparing? Acceleration. Rearrange F equals ma for acceleration.
That would be that A of B is 37.
So there's the acceleration of A. There's the acceleration of B. It's the exact same equation with A's and B's next to it. And then you can substitute things in using that first step we did. That first step, we can do some substitutions. We have the relationships between the masses. So we can substitute those in. See what happens when you make those substitutions. Sure, it totally works. It totally works. Yeah, number method, totally valid. It requires, depending on the equation, it can be this is that equation. We'll later on see what equations where the number method works, but then stuff like that. But it is, there's nothing that if it gets you there, that's a mess. This way, if you can do it, just say what'd y'all get? Huh? That's fine. B is 3/7 faster. Yeah, that's right. A is 3/7 faster. Let me see. So, yeah, let me quickly. So A should, B should be 3/7. D has 3/7 the acceleration of A. All right, so by doing this, y'all, by setting up this relationship, take these and you shove them in. Which one? This one. You shove them in there. Let's just see what happens when we do that. This is the strategy for these problems. Set up the equation in terms of the variable you want. Find the relationships among the variables. So FA, instead of FA, I'm going to put 3FB. Instead of MA, I'm going to put 7MB. Did I do weird things? Nope, that's good. Good. Oh. There we go. I don't want to jump the gun. Pull out that number to the front. All right, all right, check it out. What's the point of this? These are the same thing. This is the reason we did this. We were able to express the acceleration of A in terms of the acceleration of B. So long story short, AA, let's just kind of write this off to the side. Which acceleration is bigger? This is the trap. Now, okay, great. We got an answer. It's in number form. My next question to y'all is which one is actually bigger? Is AA bigger or is AB bigger? The key to this is make up numbers. If AB is 1, AA is 3/7. It is very easy to mix up the logic here. It is very easy to look at this and say AB is bigger or AB is smaller than A. But yeah, make certain you all can do these types of problems. I will be giving problems like this throughout this entire class. If I change variables, how does it affect some result? How do two things compare? It is a useful skill. It is a very useful skill to be able to do this, in my opinion. All right. Last thing. Newton's laws, applying them, and there's kind of a few pieces to this. Draw a free body diagram. Sum of forces in the x equals ma. Sum of forces in the y equals ma. Max equals sum of forces in x. So I got so tired of. Have you all ever, like, this is just a complete aside. Have you all ever tried to find the, like, symbols for the Greek letters in this? It's awful. There is a thing I found called AutoHotkey, which made it, if you know the name, it'll automatically, like, if you're interested, yeah, I had to set it up on my computer, but oh my gosh, it's going to save me so much time. Yeah, it's a plugin that lets you set macros for your keyboard, where if you type something, it automatically does something else. And in this case, if I type the name of the variable with the / in front of it, it does this. So AutoHotkey is the name of the thing that lets you set macros for your keyboard. Very handy. You make like a script that just has all, and I just found someone online that already set up these. If I set / whatever letter, it automatically inserts it. Anywho, if it's something you're interested in, these things are efficiency tools. All right, so there you go. Sum of force in x equals max. Sum of force in y equals may. And you do problems with this x and y components. So this is the general way to do all these problems. Let's see. Leo, Angelina, you all think you can come up with the net force problem off the fly? Let's do it. Yeah. Oh yeah. Draw a picture if you need to. You don't need to write it out more. Like, you can draw the picture for them. Yeah. All right, that's right here. Let's Ooh, how mean do I want to be? Somewhat mean. I push a box. No. At an angle of 20 degrees above the positive x-axis. What will be its acceleration? And here's where the first part's going to be so nice. Oh, a 3 kilogram box. With a force of 30 newtons at an angle of 20 degrees above the x-axis. Okay. I had to add some clarifications. I push a 3 kilogram box on flat ground with a force of 30 newtons at an angle of 20 degrees above the x-axis. What will be its acceleration, assuming no friction? Assuming a friction coefficient of, give me a number between 0 and 1. 0.5, and all the units for these things. What is this? Or is it, oh, it doesn't have a unit. No units. Yeah, I need to be, there you go. Draw a free body diagram.
So you're pushing it on flat ground.
I'm pushing it on flat ground, but I'm pushing upward slightly. Oh gosh, is this too strong? Is it gonna escape gravity?
Wait, are you pushing like this?
5 newtons. I don't want this thing to fly off the ground. I need this thing to stay on the ground.
Can you reach above the x? Well, above the x-axis would be pushing downwards, right?
No. That'll be.
Wait, that would be pulling.
I mean, you could draw the arrow
Yeah,
anywhere. Like, I could
you could draw it down there, but then that would technically be below the end.
Its acceleration. I want you to. What would be its acceleration in vector form? Give me it in vector form. I mean, actually, that's actually nicer for y'all. Draw a free body diagram. I reduced the force to 5 newtons. Otherwise, this thing might have left the ground, which would not be ideal. I need it to stay on the ground. It is so good. Yeah. Yep. For part A or part B? Check out part A. Part B. Part B does have that. Yep. All right, so first step is free body diagram. I'll give you all 20 more seconds to draw that. If your free body diagram is wrong, your entire problem will be wrong. That's why it's so important. If you don't know which way if you don't know the forces that are acting on it, and you don't know which way they're pointed, how can you can't solve it. For once, my picture will look like the problem. It is a box. So it is a box. Yeah, finally, it looks like the thing I said. It's always looked like it. You just had to be creative. Sure, it's on flat ground. All right, what forces are acting on it, y'all? Normal force. Which way does normal force point? Opposite the surface. The normal force is always opposite the surface, not opposite gravity. Don't fall into that trap as well. Do not fall into the trap of normal. In this case, it will be opposite of gravity, but that is not a guarantee. So yes, there is a normal force opposite the surface. What else? Gravity. Which way does gravity point? Down. What else? There is a 5 newtons, and this is where you have to be careful. This 5 newtons, we could say right or left. It doesn't matter, really, in this problem. We'll assume we're going to push it to the right. The result would just be whether your acceleration was positive or negative. It's fine. So 5 newtons at an angle of 20 degrees. So this is 5 newtons at an angle of 20 degrees above it. So that is part A done. I kind of read it away. Any other forces for part A? No. For part B, you will need to add something to this picture. What will you need to add to this picture for part B? Friction. So I am purposefully labeling it as green to show you all this is only for part B. Do not include friction for part A. If I tell you there's no friction, there's no friction. All right, I'll solve it so y'all can have the right answers. Yeah. It is in vector component form, so I need both. Even if it seems silly, there's a reason. It's good practice. The next one's going to be a pain. Part A is very quick. Part B is going to take a little bit.
Why would the vertical acceleration be 0?
It shouldn't leave the ground.
Because
Does it leave the ground? I hope it doesn't leave the ground.
the normal force is balancing out force of gravity, but you still have the vertical component of the force that you provided.
Yeah, so in this...
Unless we're saying the normal force is smaller.
we're going to assume the normal force will be because you're pulling you up slightly.
So you think the normal force acts like after including your upward force?
So we have MAY equals FN. We don't actually know FN.
Right.
Plus FG plus F applied sine of 20. As long as I'm not beating gravity, my box should stay on the ground.
So you're saying that you're assuming that normal force and this together are going to equal
They
gravity.
have, yeah, otherwise it's leaving the ground. So basically when it comes to this acceleration,
Okay.
is this box leaving the ground? The only way you can leave the ground is if I apply a force bigger than gravity.
Okay.
Otherwise it will always stay on the ground. That's why I had to change the force to 5
Yeah.
newtons. Yeah. So in this problem, for part A, notice that I put that the y component of acceleration is 0. That is key. You actually have to recognize, and I probably should have put this in the problem. We are going to say that this box lies flat on the ground. And the reason we know that, to lift something off the ground, what do we have to beat? Gravity. The question to you all is the force that I'm lifting with, that 5 newtons, is the y component of that bigger than the force of gravity? If you do the math, you will find that the force of gravity is 3 times 9.8. That's why I changed the numbers here. The original number I had did have my box leaving the surface. In this case, the box is going to stay on the ground. Now, technically, this would cause the box to probably like tilt, and that would cause a bunch of complications. For the sake of simplicity, we're just going to say it stays flat, even though it could technically lift a bit. This is a problem where the normal force does not equal the gravitational force. The normal force does not equal the gravitational force, and you actually have to find it. You have to know that the acceleration in the y is 0. You have to know it's not leaving the ground, and the way you know that, it only leaves the ground if you beat gravity. You only beat gravity if there's a force upwards bigger than that. Normal force does not make things leave the ground. Normal force does not make things leave the ground with little hand wavy stuff thrown in there. If you jump, it does, but yeah. You just have, it's not enough. You have to know that if you're lifting, what would a positive acceleration be? The only to do that, you have to beat gravity. No, there's no. It's a conceptual. You have to realize, oh, I can only leave the ground if, like, so if I pull this on. Look, because like I'm pulling this thing up. An easy case to prove this, y'all. Just try to lift up your chair a bit. I'm pulling my chair upwards. It is not leaving the ground. Its acceleration in the y direction is 0. Right now, it's hard to see, but I'm pulling upwards and to the right, and yet my chair is staying on the ground. You only get something to leave the ground if you apply strong enough force to overcome gravity. That is so it's kind of a hidden concept in here. Realize that AY is 0 is something you have to realize conceptually, not mathematically. Because, so normal force is how much the ground is pushing on this. Which in turn has to do with how much this pushes on the ground. If I pull it up, it is literally not pushing the ground as much. So therefore the ground, in turn, gravity is still the same. Force due to gravity is the same. Normal force is due to this pushing into the ground. If I pull this up, it's not pushing on the ground. You need to find the normal force.
You can think of it like a suitcase. Like there's a reason why
Yeah. It's a good problem like that. Yeah. For part B, you have to find the normal force. For part B, you have to find it. You have 2 equations. Set up both equations. Now, I will tell you in the second case, is my box, because I've introduced friction, will my box leave the ground? Friction doesn't magically make my box start flying in the air. So my acceleration in the x and the y direction is still 0. I don't know what the answer is in the x direction yet. I haven't calculated it. This is a bit more involved. Let me calculate it real quick and then I got you.
It's not.
No. So first version is that.
Oh, this times my normal.
Yeah. So force of friction is equal to the coefficient times that. And then, so if you solve for n, get your force of friction, and subtract that by your force.
I'm going to do 2 negatives. Ooh, what?
then
Oh, okay.
All right, this is a little disappointing. I think I. Yeah, this is good. This is one of the downsides of making up problems. You can't move the box. I'm gonna let y'all figure out why that is. Friction doesn't make the thing slide backwards. Let me give you all that hint. You'll see what I mean when you're solving it. Friction cannot make something slide backwards. It's not like if I pull something and there's friction, it makes it go the other way. All right. For part B, y'all, it's the same logic. MAX equals sum of forces in X. MAY equals sum of forces in Y. Now, our acceleration in the Y we know is 0. Conceptually, we know it's 0. So we have our force applied in the Y direction, plus my normal force, minus my force of gravity. That's how you're going to calculate the normal force, y'all. So we get 0 equals F times sine of 20 plus Fn minus, mass times mg. Fg is mg. That lets you calculate the normal force. So you do that, what do you all get for the normal? 27.69, I believe. This lets us get the normal force, which is very important. Because when we set up our MAX, we have a force applied in the X minus my force of friction. So that's my setup there. And then you all remember that FAX, so that's going to be 5 cosine of 20. There is an equation for friction force. It is mu Fn. We know mu. We know Fn. Now, you will find when you plug in numbers, that you get a negative acceleration, which is nonsense. So let's just kind of move on to another slide so I can show y'all. And this does not mean this problem is broken. It just means that the result that you get, you have to think about. All right, great. So we move this down here. So we get MAX equals 5 cosine of 20 minus 0.5 times my 27.69 equals, you plug that in a calculator, you get negative 9.14, I think. I mean, y'all tell me. Try it out, plug in the calculator. I think I got that. 13. No, it should be less. Did you all get that same normal force as me, 27.69? Five over 3? I think it's just 5 because it's the x component. So okay. 9.14? Yeah, perfect. That's what I got too. Okay. I was getting a little worried there because no one's getting back to me. What is a negative yeah.
How'd you get the normal force?
Yeah, so the way I got the normal force, because I kind of went through that quickly, is from this expression. So we know our box is not going to fly upwards or downwards. We know, just like before, we know our acceleration is 0. So with that in mind, I just set up this expression. The y component of pulling it up, plus the normal force, minus the force of gravity. And then I rearranged that and found the normal force from that. Okay. MAX, we'll put the mass in here. All right, great. I'm going to divide that by 3. You get AX equals this. And if you tell me that this is the acceleration, it's wrong. What direction is... All right, my box is sitting. If I have an acceleration of negative 3.05, if I'm pulling my box... Which way are we pulling this box? Left or right? Right. If the acceleration is negative 3.0, which way? Is that going to speed it up or slow it down? It's going to slow it down. Now, that does mean this could be moving. This could mean I'm pulling a box and it's slowing down over time. Or it could mean the box doesn't move at all. If the box isn't moving, is friction going to suddenly... Look, I start pushing this desk. Is it ever... I'm not pushing enough for it to move, right? It's not moving. If you ever push something to the right, is friction ever going to cause it to start going back at you? So in this case, the answer is actually 2 possibilities. Why wouldn't it push backwards? Friction always opposes. It never... So if not moving initially. So that's one possibility. Or A equals negative 3.05I plus 0J if moving. All right, look, don't worry about this problem too much, y'all, but it is a good thought exercise. Do you understand what's actually going to happen? That's honestly what this problem is testing. If you got the free body diagram, that's also solid. Okay. There's only 2 more things I want to remind you all of, and then... Ooh, do I want to give one that also hurts your brain? Let me do the ones that doesn't hurt your brain as much, and then I'll do one last problem. Yeah, go for it.
Can I tell them about something that I do to make it easy? Okay, so if I put this on, something I do to make it easier. Personally, could I write on this?
Go for it.
Okay.
Yeah, make it
So when we have this free body diagram, we'll have this force going this way. You can see where I'm highlighting, right? Yeah. What I like to do is when you split everything up into f of x, which is in this case 5 cosine of 20, and I'll have 5 sine of 20. Excuse my handwriting. But I just like to combine this with everything. So I know I'll also have a normal force going this way. I'll have mg going this way, and then I'll have my force of friction going this way. Over here, I can just invoke F net equals ma. I know in my y nothing's moving, so I can just set these equal to each other off the bat. So I could 5 sine 20 plus n equals mg, and I can immediately solve for n here. Since I combine my free body diagram with my force split up in the x and y, so I could set F net y and F net x. I know it might be moving in the x, so I can do my f of x minus my force of friction is going to be equal to my total ma here as well. max, not my. So this is what I like to do, so I can just see both sides of both equations in the x and the y. As long as you know both are independent of each other, you can write your equations in the y and in the x. So that's what I like to do personally. It might make it easier for you guys as well.
Yep. There's many ways to kind of view these things. They all do boil down to...
Yeah, it's the same thing, but just a different way of setting it up.
Yep. All right, so I'm going to jump to the one that's not going to hurt your brains as much, but I need you all to remember. Circular motion. I need you all to remember that the sum of forces point towards the center. So let me give you all an example problem. Let's see. There's only a couple of cases. You know what? Let's do this one. Oh, that's going to be a future one. Draw the forces. A cart goes around a roller coaster loop. Draw the forces acting on it at the top, bottom, left, and right side of the loop. So that's part A. Draw a loop. Draw the cart at the top, the bottom, the left, and the right side of the loop. And then step B. In each case, what forces combine to give you the centripetal force? Woo! There's a roller coaster loop. I care here about here, 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 and here. Draw the forces acting on it at each of those places. In each case, what forces combine to give you the centripetal force? The answer to part B will be different for every single, the exact answer for part B will be different at all points. We'll call the top part A, bottom C, left. So, it's literally a convoluted circle because of all the and honestly, there's gravity and there's gravity. Next time, set it with her down up now. Not that. Assume no friction.
Yeah, because the car doesn't have to worry about gravity because it's shady only the X.
For this answer, y'all, every single spot should have 2 arrows drawn on it. Point A, point B, point C, point D should all have, each should have 2 arrows. Yeah, we'll assume this is going counterclockwise. The direction of motion won't matter here, but it is good. If you want, assume it's going to the right. You could also assume it's going to the left. The answers will be identical. In each case, draw those forces. What 2 arrows should be in every single one of these? F, N. Now, so at point A, which way does gravity point?
Down.
Down. Which way does normal force point?
Down.
Fantastic. At point B, which way does gravity point?
Down.
Which way does normal force point?
Up.
Point C. Gravity still points down. At any point, if you tell me gravity doesn't point down, you're wrong. FG is like the easiest one because it always points down. Always, always, always. Which way is FN point? Right. Point D. Gravity points down. All right. So the key to part B is realizing. So part B says that the centripetal force, MAC, equals the sum of forces pointed towards the center. Which way do we define as positive? What is it? Is our positive up, down, or something else? Towards the center. Positive towards center. Negative away from center. All right, I lied to y'all. Part B, 2 answers will be the same. 2 answers will be the same for part B, but the other 2 will be different. So try part B. In part B, I am saying which forces equal this. So at point A, what does MAC equal? Which forces? At point B, MAC equals which force is with parentheses S? Which forces point towards or away from the center? Which forces point towards or away from the center? That is the key to doing this. This is the key to using centripetal force. MAC equals the actual forces, and you have to decide whether they're positive or negative, and which ones actually point towards the center. So just look at point A. Do any forces point towards the center in point A? And they point towards this, or are they positive or negative? You just add them together, and that equals MAC. That's it. Then you do the same for point B. Are there any forces that point towards or away from the center? Towards is positive. Down is negative. Don't even have to know. When it comes to circular motion, there's no x and y. It's just either towards the center or away from the center. Yeah, and the parts that are tangent to it, don't care about that. Yeah. Yeah. Yep. Does FG point away? So away from the center would actually be yep. FG. Does any part of FG point towards the center at all? It doesn't affect the NAC at all. At all. All right, so point A, are there any forces that point towards or away from the center? Which ones? All of them. FG points towards the center, so it's positive. FN points towards the center, so it's positive. Point B. Does anything point towards or away from the center? Yes. FN, does it point towards the center or away? Positive or negative? Positive. FG, does it point towards or away? So it's all about towards or away from the center. All right. Point C. Point C. Are there any forces that point towards or away from the center? Any arrows pointing towards the center of that circle? FN. FN, positive or negative? Positive. Looking at FG, does any part of this vector, does any part of FG point towards the center? Yes. What part of it? So towards the center would be this way. Yeah, and this is the thing that's really hard with this one. Part C and part D are a little tricky. FG has no component that points towards the center. FG, if we did problems like this, where there was like a force up here, and at that point you could find a part that pointed towards the center, we did that problem, and that's a really good problem to kind of keep in mind here. But at this spot, FG has no component that points towards the center. So the centripetal force for part C, that's it. That's the answer. FG does not contribute to the centripetal force at all when you're directly on the left or right side. Same for D. At point D, MAC equals FN. Because, looking at our picture, no part of FG points towards the center. No component of FG. It is perfectly perpendicular to that. So, there you go. All right. Y'all been doing great. There's one last thing we'll talk about, and then I think our brains will be saturated. There's one last problem I want to talk about to make certain we have covered the gambit of all the things. You're not going to like it. I'm just going to preface that. I don't know. Maybe you'll like it. There we go. This problem is a 2-for-1 special. It's a 2-for-1 special because it is both a pulley problem and an inclined plane problem. If you can do this problem, you can do both problems. It may look mean, but the reality is this is the skill sets I need you all to know. This is what at the end, this problem is both an inclined plane problem and a pulley problem. And so if you can understand inclined planes and you can understand pulleys, you can do this. And ultimately in this class, I need you to kind of understand both. For your future classes, you need to be able to think about both. So that's the logic here, y'all. It might not be fun, but but it is there. So, give me a number. 10 kilogram mass hangs from a pulley straight down and is attached to and I'm going to give you all the number for this to make certain it works, a 1 kilogram mass on a 30-degree inclined plane. All right, so there we go. 2 parts to this. 2 possible questions I can ask. Find the acceleration, assuming no friction. And I bet you can guess part B. Find the acceleration, assuming a friction coefficient of... Move this over here so it's out of the way. A friction coefficient of, let's just say 0.2. Okay. What I want you all to do, there's kind of 2 things. I want you all, we're going to have to do 2 pieces here. I want you all to draw first. You know what? Before we even do these, I want you actually to do the following. Draw the free body diagram for each object separately. I don't even want you all worrying about the acceleration right now, because that's going to be overwhelming. I want you all to draw the free body diagram for each object separately. And then I'm going to want you all to draw the free body diagram for the objects stuck together. I want you all to try both ways. Remember, I told you all these problems, you can do it 2 ways. So let's just practice drawing those free body diagrams. There's object 1. There's object 2. The good news is, y'all, we're still going to finish early, but yeah, this problem is going to kind of stretch. It's taking a bunch of things all together. And honestly, I need to include this problem in my problem sets so that you'll have this one in the future will include. It's such a good problem. It really tests if you know it. It really tests if you know a lot of things. Yeah, the numbers should all work out. And the 1 kilogram mass should be small enough.
Yeah.
No, granted, actually it'd be fine. It would just, which way will it slide? Yeah. That is a very good point. There is a very good point to this that I really appreciate someone just asked. You have to actually figure out which way these blocks are going to move. I purposely gave numbers that are kind of really far apart from each other. Which way will this thing move? Which one wins? And it doesn't depend upon friction. Which one's going to win, y'all? Is the 10 kilogram mass going to win, or is the 1 kilogram mass on the incline going to win? The 10 kilo, you have to actually think about this. You have to think about this, and it's for, if we assume friction. We're going to assume friction here, y'all. Assume friction. There is friction. It's not as interesting if you don't put friction. All right. So, we're going to say the 10 kilogram mass is going to move. That is very important for one of our forces. Let's do the easy one, y'all. This is object 2, this is object 1. What are the forces acting on object 2? Which way does it point? Always. Call it FG2. What else is acting on it? Tension, which is going to be up. All right. Great. That one's pretty straightforward. The second one, not as much. Second one, it's not terrible. It's just not as simple. What's acting on object 1? Is there gravity? Yeah. It is still straight down. We're going to call that FG1. What else is acting on it? Tension. Which way is that string pulling object 1? If you all check out this picture, I'm actually going to draw the forces on this picture to make it a little bit easier to see what's going on here. FG1. Then we have a tension that's pulling it up here. What else is acting on it? It's on a surface. There is a normal force. And last but not least, if there was friction, this is where I told you all the direction matters. The direction of friction is opposite the direction of motion. You had to realize, you have to kind of look at this problem and say object 2 is going to win. Therefore, object 1 is going to move up to the right, so friction is going to move. But if object 1 had 1 instead, friction would be the other way. And that's fine. It's fine for friction to be the other way if it's falling to the left. But it changes what's positive or negative. Okay. So there you go, y'all. That is our free body diagram for this, for our 2 objects. And then, I can translate that over here, but if you can set up this picture, that is, in my opinion, one of the hardest parts of it. Now, for part 2, I'm going to show you all when I say they're stuck together. Remember, I told you all pulleys basically redirect forces. This is a 1D problem, as crazy as it sounds. Pretend like these objects are stuck together. And to that end, I want you to kind of draw the forces acting on them. So if you can figure out if they were stuck together, how would you draw them then? And I'll of course walk you through that as well. You totally, as long as if you're like, yeah, totally got it. Because honestly, but now it's the same picture. You just rotate your paper. Yep. It's the same exact picture. Doesn't matter which way I look at it as long as you. Pretend like they're stuck together and draw the forces. We're going to say left, right is the direction of motion. And, up, down is the not direction of motion. Weird as that sounds. So left, right here is the direction that these things travel. So draw the forces that are in the direction of travel along the left, right. And then up and down is the ones that it's not traveling. Sounds kind of silly. Yeah. Yeah. So we're going to draw a right triangle. So we need to find the part of this that lines up with. Oh, nice. I love the way you drew that. You ready to do the right triangle too? So the key to this, so we're trying to find this angle. The way that you drew it. Do that in. Just think about the extreme situation. This flat here. If this angle gets flat, if my thing is really flat, does this gravity swing this way or swing this way? Yeah. Yep. So then this angle corresponds to that angle. Because as this goes down, that goes down. That's the logic I use. It helps me remember it. Feel free to just put it on the picture. Yeah. It'd be the same. That's a good idea. There's not going to be any pulleys here. No pulleys. So basically, remember y'all, in this case, our XY, this kind of left, right, is the direction of motion. The up, down, it doesn't travel up, down. These blocks are stuck on a path. So we consider left, right the direction of motion. So we look at object 2. in the direction of motion, so we look at this picture, in the direction of motion, we have FG2. FG2 pulls my system one direction. If you kind of look at this system, FG2 pulls, my thing can only move along this path. So FG2 pulls it to the right, and quotation marks, along that path. All right, great. I'm not going to, you could put tension. You could say tension pulls object 2 this way. Sure, we could put that there if we want to, but we're going to see what happens to it. Object 1, what forces are along that path of motion? There is a tension to the right. If there's a tension to the right and there's a tension to the left, what's going to happen to those tensions? They cancel out. We don't worry about them. That's why I'm not actually going to draw them here. They are in the direction of motion, but they cancel out. There's one to the right, there's one to the left. Who cares about them? All right. What else is there? There is a friction in the direction to the left, in the direction of travel. Now, something you got to be careful. There is one more force in the direction of travel. There is one more force we need to draw in the direction of travel. FG1. Very specifically, this is where you all have to remember. There's two ways you can draw this triangle. The way I drew it in class was this. Let's make it purple. Let me rewrite it here. This is where inclined planes come in. You do need to know inclined planes. There is an FG1, we'll call it Y, and there's an FG1, we're just going to call it X. There's a part of gravity that pulls the thing down. So to put it in a different color, we also have an FG1X. Great. Those are all the forces in the direction of travel. Now, there is some forces otherwise. We do have some force. We have the normal force of 1. And we do have FG1Y pointed down. We can put those on there. It's a little tricky to see. And I honestly ran out of space, so I don't like that. Through the power of copy and pasting, I'm going to make this look nicer, so if you all look at this later. All right, I'm going to leave that. I'm going to delete this. I'm just giving myself more space, so when you all look at this in the future, if you decide to look at this in the future, it's easier to read. FG1Y. Okay. Honestly, drawing this free body diagram is the hard part of this problem. After you do this, it's actually really straightforward. Guess what we're going to do, y'all? If we want to find the acceleration, MAX equals sum of forces in X. MAY equals sum of forces in Y. Drawing the picture is the hard part. After this is just using these two equations. You have your X, you have your Y. But being able to draw this picture, being able to draw this simplified like this, like you can do it as two different pieces and you can do a bunch of things. You can find tension, you can plug that into, like there, you can do that. In my opinion, there's a lot more steps there and a lot more complex. Like I think people will be, I don't know. Both ways work. But this is the one, if you can draw this picture, you're good. Yeah.
In the little triangle you drew for gravity, where is theta? Like, where is the
Yes, thank you for asking that. Thank you for reminding me of that.
So
Inclined plane. So yeah. In that inclined plane mindset, that is the question. In my triangle here, I didn't give you any of the angles in this picture. At least, not obviously. This is where you can, one, just memorize this. Or here's the logic I use. So basically, we are asking ourselves, this is 30 degrees. I'm very likely going to want to use this angle right here. And my question is that 30 degrees or is that 90 minus 30 degrees? That's the question that you're basically trying to answer. We know it's going to be one of the two. That's like always what it ends up being. And the logic I use for this, the logic that helps me remember this, like logic through this, if my angle was flat, if my inclined plane was flat, which way would this FG swing? Would this FG swing this way towards the like horizontal, or would it swing straight down? So as my inclined plane, if my inclined plane was completely flat, my FG swings towards this side. So long story short, as this angle gets smaller, this angle gets smaller. That's the logic I use to think through this. Therefore, they're the same angle. As my thing gets flat, if this is 30 degrees, this has to be 30 degrees because they correspond to each other. You can do geometry stuff as well. There's many ways to prove that to yourself, but that is 30 degrees. And I do really, really encourage you all to make certain you know that you can figure out that that's 30. And because that's 30, this is 60. There's many ways to logic through that. You all will have to kind of process through that and kind of see what works for you. But that's what I do. I just say, hey, make the thing flat and see what happens to that angle. If I make it flatter, does that angle get bigger or smaller? And use that as your check. Okay. Honestly, I'm not really too worried about like getting the... I will find the answers to these questions. So find the acceleration, assuming no friction, assuming the acceleration. I will put these answers here and I will upload this. And if you all can solve this problem from scratch, that's good. That's a really good sign for forces. That shows that you understand inclined planes and it shows that you understand pulleys together. So that's a good problem. But anywho, to that end, alternatively, if you're really struggling with inclined planes, do just inclined plane problems. If you're struggling with pulleys, do the pulley problems. I believe there's one on the quiz actually for this week. So, hey, make sure you all can do that stuff. It's useful. It's important. Pulleys exist in this world. They're very, very useful functionally. So, anyway, that's that. I'll put the answers here at some point in the next 40 minutes, but that's kind of my last jabbering. Feel free to stick around if you want to. Yeah.
So if you're solving it like the stud way,
Yeah.
and then it's together.
Yeah. Oh, yeah. That's a good point.
Then it's just an 11 kilogram mass.
Yeah, thank you for clarifying, for asking that question. Yep, because it's the total mass. Yep. Okay. Good. Yep, and the second one is just. Yes. Yeah. Yep, just like we showed in our picture, to the right is positive, to the left is negative. Yeah. Good. Yeah, we're basically framing this as, it's 1 p directed, and our y coordinate is the not straight. Yeah, so extended office hours now. Ask any questions you might have. I'll be here. I'll be here till 10:50. Feel free to stay or go, whatever works best for you. And I will upload this in like 20 minutes or something.